Hello. So this is a lecture about proofs. So we're going to introduce you to how to make proofs work. So we will go over some review of quantifiers. Let me just go back here. So go through some quantifiers. Oops, we'll have to get the pen going here. So let's get that. What's that? Let's get a color here. Okay, so I think we're ready to go. So we will talk about quantifiers and inference and lemma's theorems and corollaries and some proof methods such as direct proofs, which we have already done, and contraposition and contradiction. Okay, quantifiers, we have already seen that before. This one says for all x, for all y, so these are the universal quantifiers, that this statement is true. So for example, if I assume that x and y are in the domain of natural numbers, so let's assume that x and y are in N, so that means I know that then x plus y is going to be greater than or equal to 0, so that's my pxy. So this is true for every pair x and y that are in the set of natural numbers. This one's, we want to interpret this as for all x, I can find a y. For all x, I can find a y such that pxy is true. For instance, if I take the statement pxy, it's the statement that x plus y is 0. This means that given any x, I can find a y, which I know to be minus x, such that this statement is true. So this one says for all x, there's someone that can make the pxy true. Now this one says there exists x, and for all y, pxy is true. So in that case, I would take something like maybe 0 plus y equals y. We know this is always true, and we pick this to be our x. So this means given x, I can find a relationship between x and y such that pxy is always true. Now this one says there is x and a y such that pxy is true. So for example, if you take the relationship that x to the y is 8, we know there's an x and y such that this is true. We know that in this case, x would be 2 and y would be 3. So this explains how we think about quantification, universal and existential quantification. So negating quantifiers, if you take for all and you negate it, it gives you they exist. So for instance, if you say for all x px, the negation of that would be that there exists an x such that px is false. So if it's not the case that for all x px is not true, that means there must be some x where px is false. On the other hand, if you take something like there exists x such that px, and if you negate it, you're saying something like for all x, the px is not true. This means that if you cannot find an x such that px is true, that's the negation of it. You cannot find an x such that px is true. This means for all x, px is not true. So these two statements are really the same thing. So if you negate it, negate universal, you get existential, and vice versa. So that's how you think about negation. Let's talk about the rules of inference. Now this one says P, and P implies Q is a tautology. We think it's always true. Not we think, we know it's to be true. So if you know that P is true, and if P implies Q, then Q must be true. So the entire thing implies that. So we call this modus ponens. Now there are a whole bunch of things like that. So this is the one we just looked at. And this one says not Q, and P implies Q. So we know that if P implies Q, then not Q implies not P. Therefore, we have this outcome. This one says P implies Q and Q implies R is P implies R. We call that relationship that we can try to prove a little bit later. So we'll try to look at it. This one says if you have P or Q true, and if you know P is not true, I mean not P is true, that means it must be the Q that's true. This one says if P is true, then of course I can add any Q to that and the whole thing is true. So P true implies P or Q is always true. Now this one says P and Q, for this to be true, both P and Q has to be true, and that implies P. Of course I can replace this by a Q, that would still be true. So this is a great one because when you're doing, when you're proving propositions, you could potentially replace P and Q by just P or Q. But the only thing is you cannot go back. If you know P, that you don't know whether P and Q is correct. So we can call it simplification because we could take two statements and replace by one proposition. This is of course trivial. And this one says P or Q and not P or R. So that means we know Q or not P, P or not P will give you essentially the truthness. It's P and not P will give you false. So therefore the whole thing is depends on Q or R. So it's called the resolution. All right, so let's take a look at proofs. The notion here is to understand the proof, and we can describe methods for constructing proofs. So this is a typical thing. I'll skip through that. Let's do a definition of a proof. A mathematical proof of a proposition is a chain of logical deductions that leading to the proposition from a base set of axioms. So from a programming set of things, you can assume that these are the preconditions and the deductions is your program. So this is your computer program, and these are the set of assumptions that we will use. We're going to be focusing more on mathematical proofs in this course, not the proofs of the other kind. So a few things quickly. A theorem is fairly a statement that can be shown to be true. And if it's a theorem, we have a proof of that. A lemma is a simple statement that can be shown to be true in just a few steps. It's like a helper function. So think of theorem as your program. And these lemmas are like helper functions because you don't want your program to be too long. So you write some helper functions to get things done. And it's the same thing with the theorem. If you want theorem to be fairly concise and straight to the point, and so we use the lemmas to do that. Corollary is a result that can be established directly from a theorem. So you might say you wrote a program to do something using some helper functions, but you suddenly realized that you could get something else out of that program that wasn't your plan, but it turned out to be the case. Now these are some examples of lemmas. Notice that the lemmas are not that long in terms of a proof. And this is what you're trying to prove. Now these are the assumptions that you're making, and so on. You can see that there are few simple statements, but you don't really have to understand this. This is high-level algebra here, linear algebra. Same thing here. That's a theorem. So what we're trying to prove is that this statement here, with all of the assumptions that we are making about that. So here's another statement. So this is a two-part theorem that leads to some level of a conclusion. A corollary is, notice that it is just a free thing. You have this statement. We say we don't have to prove anything. We just follows from something. So stating a theorem is very important. So here we state a theorem, like saying if x is greater than y, where x and y are positive integers, then x squared is greater than or equal to y squared. So how do you prove that? So this is your assumption, and we want to prove this. So the ideal way to prove that is to think about this quantity here, x squared minus y squared. and you factor this as x minus y, x plus y. Now, because we know x and y are positive integers, and what we know is that the x is greater than y, and therefore we know that this quantity has to be a positive, strictly positive, right? Because x minus y is strictly positive. Because they're positive, we also know that this has to be positive, and therefore the whole thing, the product of two positive numbers, is positive. That implies that x squared is greater than y squared. Okay, now let's take a look at the other problem, which is we want to know if for all real numbers, if x is greater than y, then x squared is greater than or equal to y squared. Now, to prove this is quite simple. For example, if you draw numbers on the number line, so let's say you draw something like this. So let's say that x is -2 and y is -4. We know that -2 is greater than -4. So we know x greater than y is true. But if you take x squared, which is happen to be 4, but it's less than y squared, which happens to be 16. So therefore, this is not true. We can find a counterexample to show otherwise. So proving mathematical theorems can be difficult, and you need a lot of ammunition. And in this course, we're going to be learning about proof by induction, which is kind of similar to recursion, and also another powerful technique called proof by contradiction. So there are three types of proofs that we will look into in this section: direct proofs, proof by contraposition, and proof by contradiction. Direct proof is essentially a conditional statement. We assume P and we want to show Q. That's a direct proof. So we use the rules of inference to get there. So let's take a look at a simple example here. We want to prove that if n and m are perfect squares, then n times m is also a perfect square. So we will say something like this. Suppose let m and n are perfect squares. So this means that m can be expressed as some square of a number. And similarly, n can be expressed as a square of a number. That's a property of m and n being a perfect square. So we know the set of perfect squares are 1, 4, 9, 25, and so on. So now if you take m times n, which gives you a squared, which is a times a, and b squared, that's b times b, but we can use the properties, associative properties, to move things around, and we can get to an expression like this. This means that this is equal to ab squared, and if you assume that let ab equal to some c, this means it's c squared. And that means, by definition, it's a property that mn must be a perfect square. Perfect square. All right, so similarly, you can prove things like that. Now, this one says that you want to show that there exists no integer such that, there exists an integer such that this is not prime. The answer is fairly trivial. All you have to do is just pick n to be 41. So we have 41 squared plus 41 plus 41, which you can factor out of 41. So you get 41 plus 1 plus 1. So this is really 41 times 43. So because it's a product of two numbers, this is not a prime number. So all we have to do is find some examples to show this is not the case. Okay, so our next attempt is to prove something like this. Now, we try to take a direct approach to proving this, such that we take this to be not P or Q, and replace this by not Q or R, and we want the AND these two, and then we have to somehow show that this implies P, not P or R. We want to show implication, not the equal sign. It's possible if you expand it directly, you might be able to get things by using some of the inference rules. But the advice is not even try to do that because this is a rule. We don't even have to do that unless you want to show it by creating a truth table. So we create a truth table with 8 possible options for input, and then we will compute P implies Q and Q implies R. So we'll make a few rows here, columns, and then we will make P implies R, P implies R. And then what we have to do is to find that this is P implies Q and Q implies R implies P implies R is a tautology. That's all you got to show. So here's another problem where we have to show that if x is between 0 and 2, then this is true. So one way to approach that is to look at the left-hand side. You factor out x from that statement. You get x squared minus 4 by using these two, plus 1. And you simplify this further. This is x minus 2 and x plus 2 plus 1. Because we know x to be positive, this quantity here is negative. Because we know x is less than or equal to 2, this quantity here is also negative. And this quantity here is positive. So if you have two negatives and a positive, you get this whole thing to be positive. Now, of course, when you have a positive quantity, and if you add 1, it's got to be strictly greater than 0. So we could easily prove, notice that we use all the facts. We know that x is greater than 0 and x is less than or equal to 2. So we use all the facts to prove that. So you can go with this slowly if you like to understand a little bit more. Now this is a bogus claim, 3 greater than 2 and so on. The reason this is a bogus claim, so I'll give you a little bit of chance to think about it, why it's a bogus claim. Of course, the outcome is not right, so there must be something wrong in our proof. Seemingly, when you look at it the first time, it seems everything is good. You know 3 is greater than 2, you multiply by the same quantity both sides, and then you bring the 3 into the logarithm using the rule log of xn is n log x, and you do the same thing here, and then you can take the inverse of the log function, which is the 10 to the power function. So if you take 10 to the power log 10x is in fact equal to x. And so if you can do that, and then by doing that, then you could just get 1/2 cubed is 1/2 squared. So of course we know this to be true, so there's got to be something here. So it turns out what is wrong here is that log 10 to the 1/2 is a negative quantity. And so when you multiply by a negative number both sides, you need to change this to opposite. And so if I change this to opposite, all of this, everything is okay. So there's nothing wrong with it. We just did not realize that this is a negative number. So here's another one that is sort of a fraud. So we assume that A is B, and B are two equal numbers. And then I'm going to multiply both sides by A, so I get A squared on this side equals B times A. I will subtract B squared from both sides. A squared minus B squared, so we get AB, so I have A times B, so we have A equals B, so I multiply by A, subtract B from both sides, so yeah, BA minus B squared, so I will factor this, and then divide by A minus B. That leads to A plus B equals B, these two here, and that implies A equals 0. Now, this could not be possibly true. There must be something wrong. It turns out what's wrong is that we divided by 0 because we know a equals b. This implies that a minus b is 0. So this step in the proof is incorrect because we know that a minus b is 0, therefore you cannot divide by that. So you can see that sometimes you can get crazy conclusions out of statements if you do some illegal operation. There are two things that are important when it comes to even numbers and odd numbers. Whenever you have an even number, you can express it as 2 times k for some k. For example, if you have like say minus 24, that would be 2 times negative 12. So we know 2 times some k, that's the k, right? So some integer k. It can be positive, it can be negative, whatever you want, right? So we want to prove that the sum of two even numbers is also even. For do that, so let's suppose that we have two numbers, m. Because it's even, it can be written as 2k. Suppose you have another number, which is even, it can be written as 2l. And so if you take the sum, you get 2 times k plus l. And if you call k plus l, say r, what that means is a definition of an even number. So this got to be an even number. The square of an odd integer is also odd. So in this case, let's assume that m is an odd number. So this means m can be written as some 2k plus 1. And if you square this, you get 4k squared plus 4k plus 1. And if you take 2 out of this, then you will get 2k squared plus 2k plus 1. And let's call this some, say, whatever you want to call it. Let's call this r. So we have 2r plus 1. And that's the definition of an odd number. So as you can see, we use the definition of an even number and the odd number to get the results we want. You can try the other problems yourself. So let's take a look at a proof by contrapositions. In this case, we want to show that P implies Q, which is harder to prove. So we show Q, not Q implies not P. So this is a perfect example. Suppose we know 3n plus to be odd. And then we want to show that n is odd. But this is not very difficult to prove straight. So if I assume P, so let's assume that this is P and this is Q. And I want to show that P implies Q. But instead of that, I'm going to try to show that not Q implies not P. So this means not Q means n is even. So suppose n is even, so I have n then can be written as 2 times k. So I look at 3n plus 2, which is 3 times, now n can be replaced by 2k plus 2. Oops, let me go back here. 2k plus 2. And obviously I can write this as 2 times 3k plus 1. And if I assume this to be r, so I get 2 times r. So this means 3 and 2 plus 2 is odd. So we just proved that if n is even, then 3n plus 2 is also even. And what that means is if 3n plus 2 is odd, then n must also be odd. Same thing with this one. If n is an integer, n squared is odd, then n is odd. So to prove that, we assume that this is P. That's the proposition P, or you can call it Pn if you want. This is the proposition Qn. Let's call this Pn because it's like a predicate. This is dependent on n. So you want to show that Pn implies Qn. But what we're going to show is to show that contraposition is show that we want to show that not Qn implies not Pn. Right? So not Qn means that n is even. So n is even means n can be 2k. So we look at the square of n now. That gives you 4k squared. This means it's 2 times 2k squared. Well, let's call this r. So this means 2 times r. And we know that's the definition of an even number. So that means Pn, n squared is even. So if n is even, n squared is even. That means if n squared is odd, then n is odd. We'll take a look at the rational numbers. So one of the key things about rational numbers is any rational number can be expressed as that. So for example, 1/2 would be a rational number, minus 3/4 would be a rational number, and so on. The irrational numbers are the numbers that are not rational. So if you take the set of the real number line, so you have 1/2 and maybe 1/3 here, maybe there are some irrational numbers in between. We'll talk more about that. But some examples of irrational numbers are things like square root of 2 or pi or things like that. So let's just prove this. The sum of two irrational numbers is also, sum of two rational numbers is also rational. So let's say that we have two rational numbers. So suppose m is a rational number. We call it p over q because that's how we can express a rational number where q is not 0, which is important. And n is maybe r over s. In this case, s is not 0. So if you take the sum of these two, so if you take m plus n, which gives you p over q plus r over s, we can simplify this to be qs and ps plus rs. We know this is some number, maybe L and I don't know, Y or something, right? But this QS is also not 0 because we know Q is not 0, S is not 0, and therefore this is not 0. And this number is some integer. So this is the classic definition of a rational number. So what we just proved was that if m and n are rational numbers, then the sum is also rational. Now this is a good one to show by contraposition. So we want to show that if p is irrational, then square root of p is irrational. So let's say this is p, the proposition p, and this is the proposition q. Now we want to assume not q. That means this implies that the square root of q, I don't want to use the same thing. Square root of p is rational. That means I can express it as m over n, where n is not equal to 0. If I square both sides, which is fine, I get m squared over n squared. Right? So I know that in this case I just got p. So if m and n are integers, m squared and n squared are integers, this implies that p is rational. So what we just showed was that if square root of p is rational, then p is rational. So this means that the opposite is true. You can say, then if p is irrational, then square root of p is irrational. So in this case, we use the fact that we want to show p implies q, but show the opposite because it's easier to show. So show that not q implies not p. All right, so that's the end of this video. We'll see you in class.